Okay, so today I will introduce formally et al. As well as formally unramified and formally smooth types. So we will have these three notions, and today I will talk of types with obey them, and there will be another session where I specialize this for schemes, and we will see what we can say in this case. So the goal here is to set up differential geometry in some sense in this context of synthetic algebraic geometry. And so this will be mainly centered around the notion of formally et al. Map. So more precisely, we will have a Lex modality called formally et al. And so the intuition about them is that a formally et al. Map is locally an isomorphism. And so here local should be understood in an infinitesimal sense, but I will be more precise about this. So, okay, the intuition. Formally et al. Maps local isomorphism. Then we will have a notion of formally unramified. So this one is very easy to summarize because a formally unramified type is precisely a type whose identity type are formally et al. So this is more of an auxiliary notion to help us manipulate formally et al. So it's a type with formally et al. Identity types. And so we will have a third notion of formally smooth, which is in some sense the notion we are most interested with because formally smooth schemes are ubiquitous in algebraic geometry. And so this notion will be set up in a way that formally et al. Precisely means formally unramified plus formally smooth. So, okay, and so then in the next session, I will introduce scheme and show in particular how those notions relate to tangent space of schemes. And so how they are really about differential geometry in some sense. And so, okay. So let's start. So first, the definition. So I say that a closed proposition is dense if any of the following equivalent condition holds. So the first condition, which is let's call the closed proposition P. The first condition, which is the simpler to state, is that not P holds. The second way is to say that there exists F1, Fn in the base ring which are nilpotent, such that P is equivalent to them being 0. So this means that a closed dense proposition is a proposition that cancels a finite number of nilpotent elements. And so here I remind you that nilpotent element in some sense encodes some infinitesimal information in the ring. And so one condition which is obviously equivalent, but there exists a finitely generated nilpotent ideal I in R such that P is equivalent to I equals 0. So, okay, here I will give this as a definition. So a map is a closed dense embedding if its fibers are closed dense propositions.
What do you mean by embedding? Or why did you only talk about embedding?
So since we asked for the fiber to be in particular proposition, a closed dense embedding will always be an embedding.
Yeah.
So the intuition here is that, so if you have a closed dense embedding from X to Y, so first of all, it is an embedding because its fiber are proposition. It is closed because its fiber are closed proposition. And actually asking for the proposition to be dense correspond to asking for the embedding to be dense. And so the image here is that you start from X and Y is what is called an infinitesimal thickening of X. So it's the same as X, but adds some infinitesimal information. So
let me look at an example. Do you want to show us?
Yeah, sure. So, I mean, the very canonical example is you look at the embedding of this, where A is a finitely presented R algebra. And N is a nilpotent finitely generated ideal. So here, if we want to see that this is a closed dense embedding, we need to take a map from map 1 here and look at the fiber. But actually, in this case, since everything is an affine scheme, we can go to finitely presented algebra. And so in this sense, what we need is that A, this type, A cosmitted by N, this tensor product here, which will be the algebra corresponding to the fiber, is actually the quotient of R by a finite number of nilpotent ideal, nilpotent elements. Sorry.
Because N is generated by finite elements of A, yeah. But this tensoring here means we apply the homomorphism from A to R. That is the chosen point of spec A to these elements, right? And that's how we get back in
Exactly
nilpotent elements of R.
Exactly.
So should we make it even more concrete and say what could we take for A? So Rx doesn't work so well because we don't know many nilpotent elements in Rx. But what about Rx modulo X squared?
Yes. So a special case would be this one. So we include the point 1 in this spectrum. So here, this spectrum is geometrically, you should see it as a point with a tangent vector, which is kind of disembodied in a sense. And so you include the point in the point plus a tangent vector, and this is indeed a closed dense embedding. And here you see it agrees with the intuition of infinitesimal thickening, because indeed we start from a point and just ask some infinitesimal information. So yeah, I think that's a good example.
Maybe just to say this, you can also see it as a subset of the affine line. And on the left, we have just the point 0. And on the right, we have those points x where x squared equals 0. And then asking for an x such that x squared equals 0, asking that it is actually 0.
Yeah.
This is the closed proposition. But if I already know that x squared equals 0, then asking that x equals 0 is a dense closed proposition.
Yes. Yes. Yes, exactly. Okay, and so here we see that at least we have this intuition of infinitesimal information included here, and so from this we will define formally étal map are the maps which are in some sense isomorphic, but I will give the definition. Okay. So type X is formally étal if for all P a closed dense proposition and all triangle like this, there exists a unique filling of the triangle. So, which in our case, we say that the type of filling of the triangle is contractible. And so, yeah, so here to give some idea, it means if we are able to build an element in X while cancelling a finite number of nilpotent, this element actually corresponds to a unique, well-defined actual element in X. And yes, so I think there is quite a few remarks to do here. So the first remark is that being formally étal is a Lex modality. So yeah, one definition I should give before is that the map is formally étal. It has formally étal fibers. So, okay, and if you recall from Lucas' talk, which introduced modality, this corresponds to the modality which is called P nullification for P closed dense proposition. So we know it is a modality because you nullify types, and we know it is Lex because we nullify propositions. And so what it means for us. So it means that you have a formally étal replacement. So meaning that you can replace any type by a formally étal one, which is the best formally étal approximation in some sense. It also means that we have stability. So from some stability for formally étal types. So they are stable by sigma types. So what this means is that if you have a formally étal type and a family of formally étal type over it, then their sigma type is formally étal. It's also stable by identity types.
So in that sigma type example, the indexing type also needs to be formally étal.
Yes. It's stable by identity types, meaning that the identity types in the formally étal types are the same formally étal. And it's also stable by by dependent product over any type. So it means if you have a family of formally étal type indexed by any type, then the global section of this family, the type of global section of this family is formally étal. And from the legs part, we also get that the type of formally étal type is itself formally étal, but this I will not use here.
Yes. Sorry.
Yes.
So here, nullify the family which is indexed by a type of universe level 1 higher, right?
So I actually close the dense proposition are they form an essentially small type because you can index them by finite list of elements of nilpotent elements in R.
Yeah.
Okay. So you get out of this trouble this way. Yeah. Okay.
So for the sigma types, why does the index family need to be formally étal? I would have imagined that it will go somewhere.
I mean, other type and
it's over a point and you just take the fiber.
so any type, you have that the product for X in A of 1 is equivalent to A. 1 is formally étal. And so if we had the sigma for anything, then any type would be formally étal, which would not be the notion we are looking for. Yes.
And which of this follows from it being an modality? Sorry.
All of this follow from being a modality. So you don't even need the legs here. The legs is useful to say that the type of formally étal types is itself formally étal. Yes.
Do you have like one example which is a formally étal? Or?
Yes. So.
And also perhaps a couple of examples for formally étal.
So yeah.
Especially for those who are not familiar with the Hallmark formats.
We come like the identity and composition of the identity.
Yeah, exactly.
So let's start with examples.
Yeah, maybe even the audience can come up with examples.
Yes.
The audience. So who asked? For example. Okay.
I mean, example or counter example.
thing,
The plane might be a metallic plane.
the plane, so R to the T.
Yeah. No.
Okay. Even R to the one, so fine.
Felix. Felix. Okay, regular.
Yes, good example. We'll do a bit larger than this by saying that open embeddings are formally étales. So
Did you define it when that is probably?
Yeah.
So map is formally étal when it has formally étal fibers. By the way, you could equivalently say that a map is formally étal if given any square of this form, there is a unique filler of this square. And both are equivalent, and actually in type theory, it's fairly immediate to see that a filler of a square is a family of filler of the corresponding triangle over any point in the type here.
And
yes.
Then by saying open embeddings are formally tiled maps, this is in the same way equivalent to saying open propositions are formally tiled maps.
Yes.
So just to reformulate this.
Yes. So prove it is enough. Prove open proposition formally étal. So let P be close dense. An open proposition U, let's say. So we have a triangle like this, so it's just to prove that P implies U. We need to prove that there is a unique filler. The fact that the filler is unique is obvious because U is a proposition. So we just need to find a filler, but since we have P implies U, we have that not P implies not U. But not P holds by definition of what is a closed dense proposition. And so we have not U, but open proposition are not stable because they are negation of closed proposition. And so from this we get an arrow filling this. Yeah. Okay, so that's a good first example. So here it's very well known in traditional algebraic geometry, and here the intuition of locally being an isomorphism, an open embedding has to be locally an isomorphism. That's that agrees with this intuition.
One example. The plane or the line.
The
Line, yeah.
yeah.
I mean, it's obviously the line is not a local isomorphism point.
So A1 is not formally étal.
But actually, for you on this, can this even ever happen? So now I think, okay, usually I don't have a map from one to an open proposition. So
I mean, it means that the open proposition holds.
yeah,
So it's actually step one.
that's the.
If an open proposition is implied by dense.
Yeah. So if
then
it
actually holds.
yeah, if it holds
Yes.
on the dense.
That's what it is. So if you have that arrow, then actually the thing is one.
What it means is that when you want to prove that there exists an element in the ring that is different of zero, you can assume that a finite number of nilpotent elements are actually zero,
Yeah.
and it's a valid way to prove it. Yeah, so A1 is not formally étal. So here,
Yeah, I think this is really good reason why we are calling P dense.
yes, it's a good reason. It's also dense if you use the I mean, obvious definition of dense using open and closed. You get that the closed proposition is dense if and only if the map from P to 1 is dense in this usual topological sense.
There are like 5 different senses. Which one? That is
So if-
empty, then so is
Yeah,
yeah.
if
Okay.
its intersection with an open is empty,
Okay.
then the
No, but-
open was empty.
What do you want to, what do you want to say? If it's contained in an open, then the open is everything? I mean, that is what we have here. Right?
And they are equivalent, I think. If I understand what you say correctly. Yeah, okay, let me prove that this is not formally étal. So here everything is fine. So it's actually the same as giving as showing. So saying that A1 is formally étal is the same as showing that there is a unique filler for anything of this form with I finitely generated nilpotent. But so if there was a unique filler, we could show that any nilpotent is actually 0. So let me do this precisely. So let R be nilpotent. To consider this. So here, let's consider the map sending X to 0. We know that there is 2 lifting here. The one sending X to 0 and the one sending X to R. And so if there was a unique lifting, both of those would be equal, and then R would be equal to 0. And so this would produce a proof that any nilpotent element is 0, and this is a contradiction. I don't know if we explain why this is a contradiction already.
Well, I think we saw before that we not marked no importance, are not.
It's not the case that every nilpotent is 0.
Yeah.
Yeah,
I mean, something like this I mentioned at the top.
Yeah, okay. So yeah. So this would say that, so it's not formally étal because not every nilpotent is 0.
So, and about the intuition, so I guess the intuition could be that something like the affine line should be as good as it can be as a scheme, right? It looks very nice, but maybe the intuition were that it is smooth. So we haven't seen smooth yet, but the line will be smooth, but not étal. Étal is even more. And when you ask, is a point, is a type étal? I mean, it really means it's étal over the point.
Yeah.
And of course, A1 would be étal over A1, but not over the point.
You see my identity example.
Yeah. Yeah, I don't know why.
Same dimensions.
But I think, coming from classical algebraic geometry, I can think that something is étal without referring to the base. Sounds stupid. So, and so I think it's also here. So, and then, because this maybe the reason why the confusion arises. So I think we should really say that A1 is not formally étal over the point. And which is of course the same.
Yes.
But captures the confusion.
Yeah. It's a confusing terminology. But then on the fact that you can in this synthetic setting you can define formally étal map fiber-wise. It's like it's the motivation for just defining formally étal types and Okay, so a remark I should do, which is so here we use closed dense proposition to define formalital, but actually there was a few other choices and all of them are equivalent. And let me write this down. So let's be a type, then the following are equivalent. So the first one is X is formally étal. The second one would be for all epsilon in the base ring such that epsilon square is equal to 0. There is a unique filler when triangle of this form. So it's clear that if it's formally étal, then we will have a unique filler for any triangle of this form, because this is the closed dense proposition. It cancels nilpotent, but they are actually equivalent. So sometimes it's more convenient to check it here. And another version would be for any closed dense embedding say U2V and map like this, there exists a unique filler. So this would be the much stronger version where you consider any closed density. Yeah, I will not prove those are equivalent. It's not very complicated, but this characterization is often useful because when you manipulate elements whose square are 0, it means that you consider first order infinitesimal. And so it means that, I mean, we will see later that it means you can use tangent space and compute with derivative, which can be helpful. And actually, maybe we will see it now. So another example. Let G be a polynomial such that for x in R, we have that G of x is equal to 0 implies that G prime of x is different from 0. Then the type which corresponds to the roots of the polynomial is formally étal. So here, this condition means that we have no double root. So we have isolated roots, and so the type of isolated roots of a polynomial is formally étal. No, that's not exactly what I want to say. That when we have such a separated polynomial, the type of its roots is formally étal, and so let's prove this. So here we will use this characterization. So assume epsilon in R such that epsilon square is equal to 0. Yes, so so we want to show that there is a unique filler in this diagram. And so actually, if we look a morphism here, it's an element X in R quotiented by epsilon such that G of X is equal to 0 in R quotiented by epsilon. But actually, this gives an X in R such that G of X is equal to 0 modulo epsilon. And so I will write this here. So then you consider, say, g of x plus b epsilon. This is actually equal to g of x plus b g prime of x epsilon. And so since g of x is equal to 0 modulo epsilon and g prime of x is invertible, we can find a b such that this is equal to 0. Meaning that we can merely find a lifting, and we'll only need to prove that it is unique, but it's the same idea. Once you have this formula, it's not complicated. So, okay, and so now I will move forward. So there is a couple, oh yeah, let's move forward, but there are some examples.
So that is for Ilya's remark about several field extensions. I mean,
I'm not sure how to see separable field extension.
well, I mean, how do you construct them? Well, you take a several polynomial, which is your d, and then you just take, and of course you need to, so it's irreducible. Then you would just write down Rx of G. So covered.
Yeah, but
And if G is not irreducible, you get some semi-simple algebra.
I mean, a polynomial is not irreducible or
Yeah, right.
factorizable. But classically, yes.
Yeah, classically,
Yeah.
Capture this notion.
Yes.
Very stupid question. I don't have to worry about things like characteristic setting as well, like finite characteristics, separable targets.
Sorry, I don't understand.
Like if I'm just doing classical stuff, this is like to me. If I want to talk about like the separable extensions of finite fields, I usually have to, worry a little bit more. Zero. We have to worry about the kind of stuff here as well, like characteristic P, or is it characteristic 0 here?
So we could have, so our axioms do not assume anything about characteristics of sets. So it could be that we have characteristic P in the sense that P equals 0 in the ring R. Or it could be that we have characteristic 0 in the sense that all prime numbers are interpreted in R. But I guess here you phrased the assumption in the correct way that works for any characteristic. We have the proof for any characteristic. So it was already clear for
And that separability condition on the board is exactly equivalent to that other separability condition you sometimes learn in primitive algebra, namely that the GCD of G and G prime is 1.
That's the GX equals 0 plus GX, G derivatives.
Yeah. One direction is immediate. If we have this GCD condition, then this is immediate to check. And the other way around follows from the Nullstellensatz or from synthetic bicycle coherence, however you want to, whichever name you prefer for that.
Yeah, and then final remark, I mean, we can just cross out the line about G and then just localize the ring of which you take the spectrum at G prime.
Yes.
Which,
I write this because it seems more elementary, but all of this is the same.
Okay. That's what we said before, right? The zeros of the polynomial that happen to have multiplicity 1 in the sense that G prime is virtually there. This set is formally defined.
Yeah.
Right, because this is the same as taking the spectrum not of R S mod G, but R S mod G localized at G prime.
Yeah, this is how we construct standard entire neighborhoods.
Okay, so now let's go to formally unramified types. So I will go fast over them. So yeah, formally unramified type X in type okay. So for all P closed dense, any triangle like this, what you demand is that there exists at most one filler. Before you ask for a unique filler, here you just ask that if you have two fillers, they are equal. So remark, I mentioned in the beginning. The type is formally unramified if it's identity type. Formally étal. So here, we don't use anything specific about the closed dense proposition. It just works for any modality which is a unification. Some proposition. And so, okay. So similarly, we define formally unramified map as map with formally unramified fiber. This is a modality as well. So this is called the separated modality associated to the formally étal one. So given any modality, you can define the type with identity type, with modal identity type, and this is always a modality. So we have the same stability that we had before. And so maybe I'll go.
And an example here would be something like take a nilpotent F in R and then take spectrum of R modulo your nilpotent, which should be unramified but not étal.
If you take R quotiented by the nilpotent, it's just a closed proposition, right? Yes.
Yes. But
So yes.
if I got a
Yeah.
I mean, of course, the nilpotent should be non-trivial.
So example, actually, we can be more brutal than this because any proposition is unramified.
Yeah.
So in particular, a closed proposition. And yes, so this is immediate because you need at most one filler, but you have a position here. So okay. And let's say a remark. The following are equivalent for X type. No, sorry, but important. X is formally unramified. And X embeds in a formally étal type. So if we have that X embeds in a formally étal type, we know that formally étal type are in particular formally unramified. We know that formally unramified type are closed by sigma type and that any proposition is formally unramified. So we know that X is formally unramified. And I mean, the converse require a bit more work, but it's just a property about Lex modality and their separated type And I will not explain precisely, but what it means is that in some sense, we get all the example of formally and ramified type that are not formally étale this way. So by just considering proposition.
Is there a smallest étale completion of something formally ramified?
Yes. And that's an embedding. And that's how you prove this. You prove that so if you have a formally unramified type, you have a formally étale replacement as for any type, and you can prove that it is actually a normative. Yes, and so now I will define formally smooth type. Okay. Yeah, we'll keep this cheating a bit. Okay, so here we want to replace this by formally smooth. And here we ask not that there is at most one filler, but that there merely exists a filler. So it's very clear that formally étale means formally ramified plus formally smooth. One thing which is unfortunate is that this is not a modality anymore. And so, yes, and for the equivalent definition, using any closed dense embedding, it doesn't work anymore as well. Because let's say here you were to use any type and here a closed dense embedding in this type, you would know that over each fiber there merely exists a filler for the triangle, but you don't know if you can glue all these fibers together to create a fiber of the bigger triangle. And actually, this is the case if the type you use here has choice. And from this, you can show that the condition using the epsilon such that epsilon square equals 0 still works. But okay, I think I'm going to do it.
It was modality that co-resolution of singularity.
Yeah, no, it's not it's not a modality for a lot of reasons, and I mean we should not expect it to be. But example. So AN is formally smooth. So how to prove this? Well, actually, it's very easy. You have a map from R quotiented by N with N finitely generated nilpotent ideal. You want to find that there merely exists a filler here, but this is very simple. You just take, I mean, you know that this map is surjective, and you just take an inverse image to the image of each of the variables one by one.
And can we restrict to the epsilon squared equals 0 case, or?
Yes, we can. Okay. Yes, we can. Yes, I can explain it to you later if you want. Yes, so we still have some stability property for formally smooth, even if they are not, they do not form a modality. So, lemma formally smooth types are stable by sigma type, and another one which I mentioned, they are also stable by dependent product over a type having choice. This is not hard to see. And so, but it's not stable by identity type. And so, for example, we can see this by seeing that A1 is formally smooth, but its identity type are not. And so this I will explain from this.
Sorry.
Yes.
But by having choice, you mean if I have something like for all X in the type there merely exists, I get the choice.
Yeah, you get that there merely exists a global section.
Yeah, I merely get the choice.
Yeah.
Okay.
Open propositions.
Open.
Open propositions.
So any formally étal type is formally smooth. So open proposition now.
No, I mean for things that have choice. As an example.
Yeah. Sorry. Yeah. Open proposition.
And this
Open. No. Open proposition don't have choice.
Oh, okay.
Closed proposition.
Please, of type having choice.
Yes, of course. So X has choice if for any P from X to type such that for X in X we have the propositional truncation of P of X. Then we have the propositional truncation for all X in X, P of X. And so here, if you recall from the previous talk, you have Zariski local choice, which is a weaker version of this, where you don't have a global section, but merely a section on each open part of the thing. And so, yes, and so let's prove the following. So, say non-example. So if a closed proposition is formally smooth, then it is decidable.
So you're saying most closed propositions are not formally smooth. Yeah, that's why you call it a non-example.
So it's a non-example in the sense that we know that not all closed propositions are decidable. So you have, it's non-empty. but we cannot find the closed proposition. It's all.
For instance, the statement x equals 0 is not decided.
Yes.
But it's actually zero.
I mean,
It's not
set
decided
x
or
in
not
0.
It's not the case that all the propositions of the form x equals 0 are decided.
Yes.
Yeah, so we don't have, so we only know that do not exist no counter examples.
Yes.
So how to prove this? So we consider the map from P to not P. This is actually a closed dense embedding. So here the proof is a bit funny because you assume an element in the basis. You want to show that the fiber over it is a closed dense proposition, and the fiber over it is just P, and you know that it's closed, and you know that it's dense because you assume an element in the fiber which is not P. So, sorry, here you want to put P. You know that P is formally smooth, so you get something here. You have that not P implies P. And then this is decidable. So, how do I prove this?
We have P is closed and not P implies P.
Yes.
That's all we have for now, right?
So from this, we know that it is decidable. And so, okay, so I will not give the complete proof, but just a special case. So we know that P is closed. So it is of the form I equals 0 for I a finitely generated ideal. And so let us assume we are in the case where I square equals 0 implies I equals 0. So this is a bit weaker because here not P implies P, mean that P being a nilpotent ideal implies that it is 0. And so we just look at the case where we have 2, which is a bit weaker, but the general case follow. And so in this case, you get that I square equals 0 is equivalent to I equals 0. But from this, you get that I square equals I.
This is true for finitely generated ideals in R.
Yeah. Yeah, and I is finitely generated. And then you use Nakayama lemma. So from Nakayama, you get A in I, such that 1 minus AI is equal to 0. And so here, either A is invertible, and then I is the whole ring, and the proposition is false. Or 1 minus A is invertible, and then I is 0, and the proposition is true. So that's where you decide the proposition. And yeah, if you have IN, you can do inductively. So yeah. From IN equals 0, you decide whether IN minus 1 is equal to 0 or not, and you get through something like this. And so I will stop here, right on time.
Yeah, thank you. So,
Yes.
Do we have a Jacobian criterion possibilities?
Not completely, but not far.
Mm-hmm.
Not far. So what you expect is to have locally constant rank, and so the point that is not completely clear is that the rank is not defined it's not always defined. But yeah, okay. I think I will present a result in the next part, which is fairly close to a Jacobian criterion.
Okay, so yeah, there are no more questions, then can go